My name is David Waltzman, and I'm a Senior Simulation Product Specialist with GoEngineer. And today I wanted to talk to you about SOLIDWORKS Plastics and everything that it can do. So SOLIDWORKS Plastics is an injection molding simulation tool that operates inside of the SOLIDWORKS environment, meaning that you don't need to save any other file types or use how to learn any other interfaces. It's all with you in one screen. So as far as why you should use it, the idea is that your engineers and designers can get a better idea of their design and how it will be manufactured without leaving their desk, without waiting months on end for mold tools to be cut and parts to be made. So just some statistics to throw out there. About 80% of plastic parts are injection molded, and usually we see a range from 10K to several $1,000,000. From my experience, it seems that 40 to 70K is what a lot of people are working with. All right, so as far as the return on investment for the tool, SOLIDWORKS Plastics is one of the most simple in the SOLIDWORKS suite, in that if you're able to save cutting one tool, the software will usually pay for itself. So here we're looking at the traditional process for injection molding. All right, so we start off with part design, and then I'll hand it off to the mold group, whether it's in-house or out-of-house, and then the mold is built. From there, we go into production, and inevitably there's a defect. And from that point, we might hand it off to an in-house expert or a consultant that is a plastics guru, and they'll be able to analyze the situation, maybe find out what's wrong. But at this point, you already have several million parts, and you've spent a lot of time and money. A better solution would be to design your parts and your mold and then do the simulation before cutting the steel. So why do this? Because now you haven't lost, again, the time and money from going through production, but also your tool can still be modified, right? So you're able to go in SOLIDWORKS, change that design, and then build the best mold. So this is better than the last scenario, but really what we're striving to achieve with SOLIDWORKS Plastics is to get the simulation in the hands of the part and the mold designers themselves. Right, so this way you can make fairly large changes early on that'll impact your design and reduce the schedule. This chart explains very clearly what I was just telling in my story. So at the beginning of your process, during part design, right, the impact of change could be very high and the cost is very low. As we're moving through the phases on mold design, manufacture, part production, and launch, we see that there's an inverse relationship. So the cost goes up as we proceed through our schedule, and the amount of change that we can actually make decreases. Right? So we want to live here in SOLIDWORKS Plastics. So in plastics, we have an extensive database of materials. We have about 4,000 materials that are available to you out of the box. And you're able to build on that with your own custom materials as well. We can model all the phases of the injection molding process, going from fill to pack to warp. And if you're not in the tool every day, we have a wizard that helps you step through and get everything done that you need. Right, there's some elements of differentiation from competitor products is that it's all integrated in the SOLIDWORKS environment, meaning that it's easy to use and the interface is intuitive, and it'll get you on your way quickly. The first level is just focusing on the flow phase. So answering the questions like, am I going to get my cavity to fill? Where are the weld lines going to be? Are there any air traps? Right? So this is all on the front end, what's going to be happening, and very relevant to any designer making injection molded plastic parts. From there, we step up to more mold level issues with the premium, and that looks at things like multi-cavity molds, family molds, runner balancing algorithms, as well as some more advanced cavity features like fiber analysis and birefringence, overmolding. When we top things off with our advanced package, it looks at the warping and cooling. So this is the cooling is the cooling lines in the mold, and warpage is referring to after part ejection. Here's the breakdown of how everything bundled. Let's dive into this in a little more detail. All right, so the first step to doing an analysis is to create our mesh. For those of you that are familiar with FEA, you know that before we can do any analysis, we need to break up our solid into small pieces. So in SOLIDWORKS Plastics, we have two options. We can create surface meshes or solid meshes. So a surface mesh goes over all the surfaces and then interpolates a flow profile between them. This is a fast way to do your analysis. Then the solid mesh fills in blocks throughout our solid piece. And this is more accurate for thicker geometry. It's very similar to FEA where how you can use shells and beams, but solids will always be the most accurate. Same thing here. Within the solid meshing, we have several options. We have hexahedrals, like in the last slide, where we're building blocks. We can also use tetrahedrals, just like in SolidWorks simulation, to fill in our solid. A unique option that's only available in plastics is this hybrid mesh, where we mix triangular prisms with tetrahedrals. This is a great way to keep your mesh count down, but still accurately take into account the boundary layers in your cavity. The most fundamental plot that most of us are going to want to see off the bat is filling. So here we have one gate at the end. This is just a graphical representation of the gate. If we wanted to model gate freeze, we could actually model it as a solid and see how the plastic's flowing through. So we see that the time is changing, and we see the overall length to fill the cavity. And also look at short shots. So on this glass here, we put one gate at the bottom, and the plastic is flowing in both directions. And you see that it fills the bottom of the glass just fine, but as it reaches up, it slows down and eventually freezes. All right, so what could be causing that? It could be that the shell is too thin for the glass. It could be a different material is necessary. Maybe we need to increase the temperature of our mold. All right, or the injection pressure of our machine. All right, so there's lots of factors. And if you've been in the industry for a long time, you know that there's definitely an art to injection molding. What we're aiming to do here is to make that more accessible to the common man, or if you've ran into this already, to understand how you can make your design or your mold parameters better. We can also look at weld lines. So here we can see we have one gate, and as our part's filling up, there's going to be times that the flow front separates and comes back together. So after each of these holes, we see that the flow front connects again, and that's going to give us weld lines, right? And those weld lines are going to be structural issues as well as surface issues, right? Because you're going to be able to see that on the surface of your product. You can also look at air traps. So here we see these spheres. There's graphical spheres here, and these are showing where we get dieseling in our model. So the dieseling effect is just like in an engine. When you get a volume of air and you keep compressing it more and more, eventually it's going to combust. All right, so why are we interested here? Well, in this case, we have our air traps on these edges, which is perfect for adding vents to our mold. So now we know before building it where that needs to be. If they weren't in convenient locations, then we'd want to redesign to accommodate them to edges that are easily accessible. If the air traps are in the middle of the surface, then we're going to get blemishes, which are undesirable for our design. We can also have multiple gates in our model. So here we have two gates, one on either side, and they're collectively filling up the cavity. There's no limit to how many gates we can have. It's just going to cost more to make the mold. Also, the more gates you have, the more you're forcing weld lines to exist, because by definition, the flow fronts have to meet. We can also view the contribution from each of those gates in the model. So if it's not fully symmetrical, or here you're seeing these triangles, these are the actual elements that are being filled. You can analyze the multi-cavity molds. So here we have two parts that are identical. We're just injecting two of them. So we've created our sprue and runner system in SolidWorks Plastics, just based off of a simple sketch. And now we can measure if the injection pressure is enough to fill our cavities. Here we have a family mold. All right, so there's two different parts here, and we see that this one is filling up before this one. All right, so this isn't ideal, because that means in terms of cycle times that their packing and cooling are going to be out of sync. All right, so in SOLIDWORKS Plastics, we have a runner balancing algorithm. So in this case, it took about an hour to chug through and change the dimensions of our runner system so that they fill up in the same amount of time. So when you're setting up this analysis, you choose max and min diameters for your sprue and runner system, and then how closely they have to match at the end for the fill. We get great outputs like shrinkage. At the end of the day, what we really want to see is warp. All right, and warp is a result of non-uniform shrinkage. So we know shrinkage is going to exist, but if we can see what it's going to look like beforehand, we can make more intelligent decisions about our part design as well as our mold. Here we're looking at sink marks. So on the back of this piece, we have ribs, right? So if you've ever designed with ribs, that'd be immediately obvious to you. Well, what you would also see is that there's dramatic changes in sink from this rib to this rib. So based off our designer's handbook, we know that there's rules about the thickness of the rib and the radius of the base fillets and how they impact sink. All right, so again, we're able to measure this before going into production. This is invaluable for checking your design criterion. You can also look at cooling times, right? So now this is in the pack phase, right? So all the plastic is injected. How much time is it going to take for our part to cool off? We can also track nodes in our cavity and measure the temperature with time. Here you see we have our different phases and how it's dropping. Overmolding is well within the capabilities of the software as well. So here we're looking at a toothbrush, and a toothbrush usually have a hard, hard white plastic and then a soft rubbery grip, right, for you to hold. So we're able to break out those cavities in SOLIDWORKS Plastics and just look at this overmold. When we're doing that, we have to be conscious of the properties of our base plastic as well, right? Because if the new plastic we're shooting in is at a higher temperature than the melting point of our base plastic, we're going to get some dimensional instabilities as well as some interesting chemistry at those interfaces. So we want to minimize that and design accordingly. We can also overmold over metal. So here we have a connector with copper pins, and we're filling up our plastic connector around the pins. All right, so this is important because for the metal, there's thermal effects that are going to change how the heat's spreading through this part. Again, looking at interface temperature, we could get more insight to what's happening inside of our part. This would be pretty difficult to measure in the lab. We also have co-injection at our fingertips. So here again with the brush, we have a skin and a core material. All right, so we can see that in this region, the core material doesn't touch. So we probably want to adjust our parameters so that we get one cavity reaching all the way across with our core material. We can also look at our effects on the outside. So during the neck here of our brush, we see that there's some core material that's made its way out. So we might need to thicken that up for the future so that it's all red on the outside here and our skin material is what's being shown. The fiber analysis allows us to see as it's filling the direction of any defined fibers. So if you're paying attention to how it's filling, the direction of the fiber is normal to the flow front or in the direction of flow. Right? So if you're dealing with let's say a glass reinforced nylon, right, you'd be able to measure the effects on the stability of the model with and without the fibers. We can also look at optical properties of our injection molded part with birefringence. Birefringence is the phenomenon of double refraction, right? So when you look at a prism and you see all the rainbow come out of it. So if you're injection molding any optical setups, this would be relevant to you. Gas assist, another great feature that we have for injection molding hollow parts. So in this scenario, we're injecting a specified volume of plastic and then backfilling it with gas, at which point the plastic shoots out to the walls and you have a hollow part. We can also model valve gates. So here you see the time release of the valves. So the one on the left triggers first, the one on the right waits, and then goes afterwards. So in this way, you'd be able to measure the contribution from each gate. So this would be an application to controlling maybe where weld lines are, or just how it's filled up. Why we're all here is to look at the warp of our plastic parts. Here the wireframe shows the original position, and then we see where the product warps to afterwards. Now, if we want to model more of the mold, we can create a virtual mold with our cooling lines in it. And again, these can be created from simple sketch entities inside of SOLIDWORKS. You can control the fluid and the flow rate. And what SOLIDWORKS is going to do is see how the presence of that fluid affects the temperature profile through your mold, which of course should change the warpage on your parts. Here you have some validation studies comparing SOLIDWORKS plastics to real life. A common question is, how accurate is plastics? So we don't have one number to describe that. A lot of it's going to depend on your setup as well as your empirical data. All right, so here we can see as we're filling up, pretty similar characteristics here, even the shape of the profile. And as it continues, it tracks pretty well. You're looking at a watch face. Again, great indications. So if you say, well, it's not exactly the same. Okay, but the goal of using concurrent design validation in SOLIDWORKS is that as you're designing, you can make the best design possible before moving forward. So let's say that it usually takes you 3 times to iterate your mold before you get it spot on. By integrating SOLIDWORKS plastics, maybe you can reduce that to 1 or 2, so that you're, again, able to work bigger, better, faster. Then here's some more complicated geometry and seeing how things fill up in this family mold here. Pretty neat indications. Also, looking at where the weld lines exist becomes more obvious, right? So if you're able to notice the change in color right here, SOLIDWORKS nailed it. So in summary, it's best to use plastics early on in the process and help you define your parts and your cavity and mold better. Sometimes we might overbuild or make a design decision because that's the way we did it in the past, but now we can explore the frontier and still improve the part quality. Now let's dive into the software and see what it feels like to run through SOLIDWORKS Plastics. So here I have a cavity, and we're going to be filling this in SOLIDWORKS Plastics. So I just hop over to my Plastics tab, and the first step is to create a mesh. So in this case here, let's create a shell mesh. And SOLIDWORKS has a fantastic auto mesher that's going to look at the cavities in the model. So here we only have one to look at. And let's just say mesh. It goes pretty quickly. You'll see here that it put one element through the thickness. Usually we want to have at least 2 to model the flow. So we'll just change our size here. This is a 3mm thick wall. So let's change it to maybe 1.5. Should generate fairly quickly, and we see now that we have 2 layers of elements. And in case we're not sure if the size was appropriate or not, it shows us if we have any bad elements, what the max aspect ratio is, the longest to the shortest dimension on our triangles. So it looks like we're good to go. All right, now that our mesh has been created, we now have access to our tree in SOLIDWORKS Plastics. So the next step we're going to do is to define the material for the plastic being injected. So here's that library I was telling you about. This is completely separate to the SOLIDWORKS CAD library. All right, so under ABS, we have over 500 types of ABS. All right, so if we don't happen to have the one you're using, again, base it off of one of these and change a couple parameters you know. We also have all these other categories of materials. So you should be able to find what you're looking for. All right, so that's defining our material. Now let's move on to our fill settings. So SOLIDWORKS, from looking at this geometry, has come up with an estimated time to fill. But if you're more intimate with the process, you could say, well, this really takes 1.5 seconds to fill. And that'll override. Our melt temperature here is taken from the material that we define. So this is the melting temperature of ABS. And then we can control our mold temperature, right? So this is just a recommended value, but we can increase it if we need our plastic to go farther. Obviously, the higher we put the mold temperature, the more warp we're going to get at the end of our process. And then our injection pressure for our machine is right there. So very straightforward setup. The more things you know, the better, but SOLIDWORKS Plastics still allows you to run an analysis and use default settings so that you can get results and again, make the best possible choice. For packing, we can set our pressure holding and cooling time. Right, so in the pack, after all the plastics enters the mold, we still keep backfilling it to make sure that everything is in there nice and neat. And for warpage, the only thing we really need to consider is the ambient temperature of the room. Right, so there's two components of stress we're looking at for warpage. One is in-mold residual stress, and the second is thermal quenching stress, which is that thermal shock as soon as it hits this 30 degrees. The last thing we're going to do here is define our gate location. So I'm going to put it on our edge here. And now our plastic will be coming in and filling up our cavity. All right, so let's hop over to one that I ran earlier today and look at some of those great results that we saw in the presentation. So looking at our flow, there's going to be a whole variety of plots that are generated. Okay, and if you're not in plastics, know all the jargon, we have this excellent advisor that opens up on the side here, and it explains real succinctly with a traffic light, was this part able to be made successfully? So here it says it only took under 20 megapascals of pressure. We had 100 megapascals at our disposal, so this filled up no problem. We could probably even go to a smaller machine that's not as powerful. And then it goes through and describes what fill time is and how to use it in the software. So great usability from our advisor. You can look at the temperature at the end of cooling, ease of fill, no problems at all. Go on to our packing phase. So we see the pressure at the end of packing, meaning that all of this should be stable by the time we're done with that. We can look at the stress in our model. As far as the warpage goes, and looking at the in-mold residual stress, that's going to be this one right here. So it's fairly low, this example. This is a well-made part. So my favorite at the end is the warp. Right, so this is exaggerated right now. So let's look at a scale of 1. So the max warpage in this case is 0.5 millimeter. Right, so this wireframe again shows our original position of the cavity, and we can see how it moved afterwards. So this would be critical if maybe there's two parts that have a snap fit, and you want to make sure, are they still going to snap together afterwards? Or if there's an envelope that this product needs to fit in, and now it's warped outside of it, that could be an issue. But to get a clearer vision of how it's warping, we can exaggerate it. So here I'm doing 20 times exaggeration. We could see how the product is moving. So the walls are coming in here, coming up there. So this is great information, again, to have before building anything. You could also isolate our components of stress that we're interested in to just the in-mold or the thermal quenching. So now that you have all this data, how can you be productive? From this warped shape, we can actually export this to another configuration or a dummy solid file, right? And use this to change the design of our part. We can also export the negative of the deformed shape. So let's say you have a flat bar and it comes out as a sad face. So in order to get a neutral position at the end, maybe you change the design to be a smiley face. And now when it warps, it relaxes back to that neutral position. Right? So this is SOLIDWORKS Plastics and how it integrates into the SOLIDWORKS environment. I hope this was informative for you, and that this could be of use to you and your teams in the future. Thank you for tuning in.